All right, it's been a great afternoon so far. Thank you so much for all your attention. And after this talk, we're going to go into a break. Ritesh was showing Grafana in his talk earlier about BGP. So we have some great open knowledge there from Sem. How about some open source to move it up? So my next colleague here is Nikola Grcevski. He's a principal software engineer at Grafana Labs. He also hosts Grafana and Friends, a meetup here in Toronto. If you want to learn more about him, about Grafana and eBPF, he's a great person to talk to. He's going to be talking about slashing network costs with eBPF network monitoring. So take it away, Nikola.
All right. Everyone can hear me? Yeah, it's good. All right. So this is probably going to be a little bit up the stack. I see a lot of people are more like hardware here, cables and whatnot. None of that stuff here. It's all software. I apologize for that in advance, but hopefully you'll learn something new. I don't know. So yeah, what I'm going to talk about here today is a specific thing that we at Grafana Labs had struggled a lot with because we try to make our software as cheap as possible for the end users, maybe increase our profit, maybe make it cheap for the end users. But apparently, cross-observability zone traffic amounts for about 25% of people's network cost in cloud. So what does this mean? So they teach us that we need to make our applications resilient so they don't fall over if a zone in Amazon just goes down, that you have to have cross-AZ availability. But they charge arm and leg for that network traffic between them. So it's good to know how much of this cost you can maybe optimize, how much of it's really needed. And so when you go on the cloud vendor and you start to collect all this data, they give you logs and they'll tell you, okay, well, this is how much you're getting between these zones. But there's not enough granularity in there to kind of figure out where they came from. A lot of our users and ourselves use stuff like higher level concepts like Kubernetes. So that's like several levels of layers removed from like hardware. And so which part of this Kubernetes workload is touching the additional zone is doing this kind of expensive and lengthy network calls. It's kind of hard to tell, especially if you have complicated setups. So I would like to improve the bottom line ourselves and also for our users. And we like to do this with as little effort as possible. So I like to go on instrument, add stuff, and so on. So this comes to kind of the topic of technology we're using to build this. It's OSS. How many of you have heard of eBPF here? Anyone? Oh, OK, so there's some people. All right, cool. So for those that don't know, like let's say we have this typical, I'm talking really software now, no hardware. I'm installing Linux. I have a kernel on there. There's some OS runtime. There's syscalls maybe you can make to it and so on. And on top of it, we have the libraries and applications. All right, so the eBPF solutions that come in play here, typically what people use eBPF for is to build observability into the Linux kernel. Maybe they add security layers to it, kind of reject or maybe monitor malicious activity. And a lot of them do networking with it. So they can optimize the flows within the kernel for specific network paths and so on. And so how does this actually implement it in the kernel? There is a separate part that ships with every Linux kernel since, I don't know, version 4 something, which is this eBPF technology, which started from BPF, stands for Berkeley Packet Filter. Started as a packet filtering technology at the kernel level, but then it got expanded into generic programming sort of virtual machine that sits into the kernel where you can program. So unlike traditionally kernel modules, which can destabilize a kernel, this actually has a verifier and a compiler and so on, and it makes things like if you drop something into your Linux kernel, it will not crash it. It will not break your setup, which is why we like it. So what kind of stuff that you can plug into? So you can plug into the network layer at Linux. So this named as N here in this slide. And then you can stick this also kernel probes, or U probes stand for user probes. So these kernel probes you can plug into, let's say, various functions in the Linux kernel. You can pick a function, go on github.com/Linux, find a function in the Linux source. Presumably it's not inlined by the compiler. You can stick a probe in there on enter and return. You can find out a lot of stuff that the kernel is doing. So it's like kernel tracing, but you can run it in production. So why is this so good for us? We want to observe network monitor a network from the Linux kernel perspective. No need to rebuild any applications. just there. So if you have application working on top of this, even Kubernetes and pods and whatever on top, it doesn't matter. No need to redeploy any services. You can just drop it in and remove it with a single install and remove command. Whatever you build as a program with eBPF gets natively compiled to the x86 or ARM architecture. So it runs at full speed, knows some interpreter stuff. And finally, they have this verifier component that everything you build, it actually runs through the verifier. It won't let you even load in the kernel if they think at least some part of it is unsure of. So every access to memory is checked. It prevents for a large number of instructions, for a large number of stack being allocated, none of that stuff that could potentially cause a problem in production. The downside is not magic. It does require a lot of low-level API knowledge of the kernel. It does all these things that you need to kind of, if you patch things and you look at data structure, you need to know the binary representation. And finally, the eBPF programs, because they're not supposed to destabilize a kernel, are limited in size and functionality. So you don't have loops, for example, because adding a loop on something important in a kernel would be a bad news. All right, so what we built here, this is an OSS product. We added network monitoring in the network layer, and we have, with K-probes and U-probes, application level monitoring. So we check, for example, level 3 and level 4, and we produce flow information. So this particular packet went to this IP on this port, and so on. It will check stuff like TCP retransmits and DNS calls and things like that. And the one that's interesting for this topic here is the interzone bytes. So I'll get to how we actually compute that. So when you take this tool and you generate this data, presumably, it can go to whatever your favorite databases. Here I'm using Grafana products for this. They're all OSS, so Tempo and Mimir. Mimir is a sort of Prometheus that can run distributed. And Tempo is a tracing database, so you can push this with OpenTelemetry and then build dashboards for network or whatever else. All right, so how do we instrument our network? Again, so I'm presenting the levels that I care about here, that I work with. So at level 3 and level 4, we typically have this kind of information. We use traffic control or socket filters, depending if somebody else is listening on traffic control. We can't plug in and chain with them. Then we switch to socket filters, which are a little bit less efficient. But we collect stuff about IP ports, packets, bytes, and so on, Ethernet addresses, interfaces on which interface on the Linux kernel you went, and so on. And as you go up the stack, there's different parts. So for example, finding connection status, host names, you need to use some K-probes, and eventually at a higher level, for certain applications, we use user space probes to capture like TLS traffic and SQL text and whatever people need. Now, and the actual instrumentation, what happens for different kind of programming languages is slightly different, but yeah, sometimes there's libraries, sometimes there's generated code. All in all, combination of some of these works in every case. So what can we monitor? So we can monitor application level data with application level protocols, low level or level 3 and level 4 metadata. This is where we focus today. And we look on how we can enrich this data so it can actually make sense to the end users, right? So why end users? Because let's say I use Linux traffic control and we capture this data in production and we have a nice flow table that tells us IP addresses. And we pick this IP address here, and then we can see, OK, well, these two are talking, and that produced a single flow of bytes that we can tell our end user, OK, for this, there was a transaction between these two IP addresses, and it did this it kind of ran this many bytes back and forth. Now, this is cool, except, you know, it has a lot of information we can use. But for our end users, at least the ones that we serve, this is very basic. Source and destination IP address, some packet count byte sum, but how would they know what to do with this information? And this is the part that we try to take a level further and see if can we enrich this information with higher level concepts to make sense for people. All right. I'll show two things here, how we enrich information, but there's possibly more that can be done. So Well, from the eBPF set, like I said, we stick, for example, Linux traffic control, and we'll start monitoring traffic. And this is what we see in the flow bytes. But what people want to see is typically something like this. I have a front-end application, and that is talking to my database, and is this namespace storage. And so they want to find out who's talking to who. Because for them, like the source destination port and source port don't mean much. So how do we get this? Essentially, what we've written, because with the eBPF side, you have this maps and ring buffers and whatnot, where you can export the data from the kernel, reaching the user space. So our user space program for this purpose is written in Go. And so with this user space program, we collect all these events, and we try to correlate them. But at the same time, we wrote a Go client that talks to Kubernetes API and extracts information from there about the pods, the services, all the concepts and metadata that exist in this world. And fortunately for us, Kubernetes does keep information about which IP address is related to which service or which pod and so on, or which node on the cluster. We also collect process ID information, and we keep them in memory. So as network flows come through from the ring buffer from kernel into the user space, we map it into the information with a higher level concepts, and from there they get matched against something that the end user can make sense of. So the other concept that we use is reverse DNS. And this is trickier than it sounds, because if I just ran this on my machine and I wanted to see go ping golang.org, and I try to do the reverse lookup, I get something completely different. So it's not reliable in the sense that it resolves the various things on the network, the way it's structured. And so what do we do for this? Again, eBPF comes to a rescue, because my instrumented application that I've dropped this on eventually is going to do a DNS call. And because this DNS call is going to be a network call, whether it's like UDP or TCP, is going to have to go through the kernel. When that happens, it goes on port 53, and it says what name it wants to resolve. Eventually, from the DNS server, we're going to get an A response or a quad A if it's IPv6. So with this, we capture the information, again, IP to data address. So this then gets collected by eBPF, and then gets shipped to the same kind of map that we called information from Kubernetes. Similarly, it's not presented here. We capture metadata from cloud vendors. Because cloud vendors, if you're running on a VM instance in the cloud vendor, they'll give you a lot of metadata about what that instance is for. And maybe you, as somebody who's deploying this, will put labels on that instance as well. So we collect those labels, again, just like Kubernetes, put it in maps. And as flows come through the network and through eBPF from the kernel to the user space, we map those up. And then we ship them to our final destinations, which are these databases from which people then build graphs and dashboards, visualizations, SLAs, and whatnot. So for this particular flow, we'll see that we had the destination IP address, but then we can derive the destination name. So how do we actually go about finding the availability zone and what people talk to eventually? So from Kubernetes, there's this pod information, and in this pod information, we have the IP addresses, which is the stuff that we use to kind of correlate to a pod. But then, fortunately for us, most cloud vendors, or the ones that we work with, in the node name, they actually put this label, topology Kubernetes IO zone, which actually gives us information about which zone is this pod into. Again, we collect these labels, and then from the IP addresses, we're able to actually make the mapping back. So when eventually we produce this information and we enrich it, then the network flow bytes, the network flows metric contains source zone and destination zone. And then we also put this interzone bytes separate collection, because some customers want to just look at this information, not the actual flow bytes. They're not interested about the network traffic. They're interested in the just cross-zone traffic. And this is kind of like from our docs, changes every day, more or less, with new stuff being added. But these are kind of attributes you can enable. There's a lot of hidden by default. And the reason why we hid them is because of cost. For a lot of people, if you have a large network, a lot of pods, a big number of clusters, and big number of nodes per cluster, choosing what you need is important because as you monitor and collect more, you start to pay more. So let's see what that looks like. So with this config in this product, you can actually choose which attributes you're interested in from the previous collection. So if I look here, there's a number of these attributes. Then I can go in here, and then I can, in this config, choose what I want to see. Not for just network, but if in the care, for example, you're monitoring application level stack, you can choose for HTTP to see the pod names or the zone for HTTP and so on. All right, so what can you do with this data? So this is part of Grafana. You can build dashboards that, with this flow bytes, then you can kind of see who's talking to who, build node graphs and so on with amount of calls per minute or calls per second. You can put colors, whether it's this zone or that zone. World's your oyster because the information is actually in the underlying data, in the underlying data sources. So let's look at one specific example. So when we first developed the software, we said, do we as Grafana actually have this problem? So we plugged it into our dev cluster, which is all I'm allowed to show here because I shouldn't be showing the production cluster or how embarrassing it is. But as soon as we dropped it in, we immediately found out that we actually had a misconfigured application that was constantly talking to a remote zone. This was a surprise to us. We have all checks and balances, we have tests, we do all these things. But you drop something in, and it works. And so it had the namespace of the wrong zone in the config, and it still worked. But it's dev environment, whatever. So if you can see that this cluster dev 0 was completely had misconfigured zone for one of those databases. So with this kind of query in Prometheus, you can actually find out which potentially what things in your cluster. In this case, we're just looking at this destination zone information, but you can find out a lot. Then this ended up being actually 4 figures a year. Like I said, I'm not saying how much it costs in production, which are much bigger clusters. This is just a dev cluster. So, but I've heard people even like 5 to 6 figures a year spend on network traffic between zones, which is completely misconfigured. Then you can get more information by then splitting up and trying to find the flows and figuring out exactly, now that I know that I have a problem, then I can go and put this additional query and then find out what pods or services are talking cross zone. And I can go and find out, oh, well, that has a wrong config, or that shouldn't be doing that. Well, I can save money. So then you can clearly kind of see that there was one particular one that was doing most of the damage in terms. Okay, so one other thing I want to mention. So this was an Oasis project I worked on when I started Grafana about 3 and change years ago. Since now this is actually being donated and exists in CNCF. It's a CNCF project now. Grafana donated it. It's called Open Telemetry eBPF Instrumentation. It's not owned by Grafana anymore, even though it was OSS. And it's maintained by a multitude of companies. If you are interested, these are the links to this project. If you care about this stuff, you can get connected. This is what most of us work on in Grafana now, this lower open telemetry eBPF instrumentation. And Bela is just a shell around it with some specific Grafana cloud things. That's it. Thank you.
We got lots of time for questions. Where are my low-level monitoring people at? Or my Rust people, or eBPF? There's some people are like shy to admit they're into Rust code.
That's
okay.
okay.
Well,
Yeah.
thanks so much again,
Yeah,
Nikola.
you're welcome. Thank you.